I thought I was going to be the other one.
You know, if you were the only one here, we'd have to increase your tuition because it would be like a private tutoring. So he just saved you a bunch of money.
That's good.
That's your tattoo.
It's healing well. I picked off the like dead cells right here.
Mhm.
It's healing great. It's there forever, so. I think it's very good. I'm with it.
It's all that matters. Do you have other ones?
No, so this is the first one.
Okay.
Thinking about getting this. It's a really bad drawing of like a chicken,
Mhm.
like a baby chick. It's got a cowboy hat on and a gun.
What's the significance of
It's a
that?
cowboy chick. It's very funny and it's a very cartoonish. I kind of want it. Just don't sell the borders out, but I kind of want it.
Okay, we'll go ahead and get started. Can the people on Zoom hear me and see the slide?
Yeah.
Thank you. So what we're going to do today is we're going to finish up chapter 15. And then if we have time, we'll start on chapter 16. The big thing I want to remind you of is that on Thursday of this week, we'll have a quiz, and that will cover, hold on a second. We'll have a quiz on Thursday of this week, and that will cover chapter 15. And so on Thursday, we'll start the class with a little bit of lecture on chapter 16, and then maybe about 20 minutes or so in, I'll stop class, and then you guys can take the quiz. So once again, finishing chapter 15 today. If we have time, we'll start chapter 16. And then on Thursday of this week, we'll have some lecture on chapter 16, and then we'll go ahead and have the quiz on 15. All right, so where we left off last week was we were starting to talk about some additional calculations regarding equilibrium concentrations. And we had done a type of this calculation before where we had a little bit more information. And so the calculation was a little more straightforward. What we're going to do today is we're going to talk about how to do that calculation when you have less information. And this, as you recall, that got us to where we're going to have to use a quadratic equation to solve that. And so we want to review that math a little bit. If you're really good at it, great. You know, this will be a piece of cake for you. If not, I want to go through it a little bit more, and then you'll need to practice a little bit to make sure you're comfortable with it. So what I do want to say though is, remember there was the one slide that I think I put up about 20 times. I kept saying this is a good slide to get comfortable with in terms of the thought process for how to do this type of work. That still holds for what we're going to talk about today, that same idea. And you'll see the box, so to speak, that we created and then filled in different pieces of information. Still going to have that approach. At least I would encourage you to do that approach. I think it just makes it easier to kind of organize these types of problems and do them. So let's go ahead and look at that example we were about to do last week. So in this example, we say we have a 1 liter flask and we have 1 mole of H2 and 2 moles of I2. And then we're given the equilibrium constant as well. And so what we want to do is we want to calculate the equilibrium concentrations for the products, the reactants of the products. And so for this type of problem, there's a couple things we have to remember. One is all the concentrations need to be expressed as moles per liter. So in other words, molarity. This one's a little bit easy because we're told it's a 1 liter flask. So the moles divided by 1, there's really no math to do that. But a lot of times you don't have a 1 liter container, you have some other volume. So you have to take your moles and divide by that volume to get molarity. The other thing that's important to have, and we have it here, is the balanced chemical equation. So in this case, it's H2 plus I2 going to 2 moles of HI. And what's important about that is we get the stoichiometry from this balanced equation. So we have that coefficient out in front that tells us how many moles of a molecule are involved in the reaction. In this case, H2 and I2, there's just 1 of each, but there's 2 moles of HI. And so that stoichiometry is used to write the equilibrium expression. And remember, the equilibrium expression is simply products divided by reactants. And then each of those concentrations is raised to whatever power the coefficient in front is. So in this case, H2 and I2 would just be 1, and HI would be squared. At the bottom of this slide, you see that box that we created before, similar box. And so let's take a look at that again. So over here on the left-hand side, we have initial concentration, and that's expressed in moles per liter, molarity. We have a change in concentration, and then we have the equilibrium concentration. So that's what each of these rows are going to represent. They're all molarity, moles per liter. And so in the columns, the first column is the H2 concentration, second one is I2, and then the third one is HI. And we see that we started with 1 mole of H2, 2 moles of I2. It's a total of 1 liter. So 1 divided by 1 is 1, 2 divided by 2, 2 divided by 1 is 2. And so for molarity, H2 initial molarity is 1, I2 initial molarity is 2, and then of course HI is 0 because we haven't started our reaction yet. The next row is that change in concentration value. So when we did this before, we had some actual numbers to plug in there, and we could do it that way. In this case, we don't have any numbers. And so what we're going to do is we're going to define how much H2 and I2 are used, and just use the variable X to represent that. So we know from the balanced chemical equation that H2 and I2 is 1 mole of each of those react to give us 2 moles of HI. So if we define that as the H2, some amount X is reacting, and that same amount of I2 is reacting, both of those will be X. We have a minus sign on there. That minus sign is just to indicate that those are reactants, so it's being used up. The HI, we have a plus in front of that, a plus sign in front of that term, because we're forming it. So that means that's increasing. And so that value is 2x, because we know for every X of H2, X of I2, we get 2 of the HI from our balanced chemical equation. So now we've got our changes worked out. So then what we can do is we can express an equilibrium concentration for the reactants of the product based on the initial values and then based upon these changes. So for the initial concentration of H2, it would be 1 minus X. For I2, it would be 2 minus X. And then finally for HI, it would be 2X. So once again, we're subtracting from the reactants because we're using those up. And the product is going to be a positive number because we're forming that. So now that setup should look familiar to what we did the other day, because it's the exact same thing, same thinking, same all that stuff. The only difference is we got all those X's in there. And that makes the math a little bit more, I won't say harder, but it just takes a little bit more time to weed through it. Okay, as I said, we can set up our equilibrium expression, HI squared divided by H2 and I2. All of those are molar concentrations. That's our equilibrium expression, products over reactants, things raised to whatever coefficient is in front of it in that balanced equation. And then we plug in those numbers from our table. So remember in our table, we had 1 minus X, 2 minus X, 2X as the equilibrium concentrations for our reactants and our products. And so we plug those in, so we have 2X squared over 1 minus X times 2 minus X equals our equilibrium constant, the 50.5. And then we would need to solve for X using that quadratic formula. And so let's take a look at this, what we're talking about with the quadratic equation. So if you recall, you want to get your expression set up to this generic ax squared plus bx plus c equals 0 format. And then we use that a, b, and c, those terms, to fill into the quadratic equation which is x equals minus b plus or minus the square root of b squared minus 4 ac. That all divided by 2a. So we got a lot of stuff we got to put in there. And so if we do the math correctly back here, and at the end, towards the end of the class, I have an example of one of the homework where I'll go into real detail on how I did the math. But in general, on this one, think of it as, let's look at the denominator. So 1 is multiplied by 2, and then 1 is multiplied by minus x. Then minus x is multiplied by 2, and then minus x is multiplied by minus x. So that's the multiplication you're doing in that denominator. The numerator is just 2x, that quantity squared, so that'd be 4x squared. So if you do all that math correctly and then rearrange, because remember we said we wanted to get things in this ax squared plus bx plus c equals 0 format to be able to plug that into the quadratic equation. It's 46x squared minus 151.5x plus 101 equals 0. So I would strongly encourage you, in this example, to go and see if you can take the math that's in this expression and come up with this 46x squared, et cetera, equation. Then we now know that the A term is represented by 46.5, the B term by 151.5, and the C term by 101. We plug those values into that quadratic equation, okay, and that's what we have down at the bottom of this slide. And once again, make sure that you can do that math, okay? And by math, I mean literally plugging it into your calculator and doing the calculations on the calculator in the correct order so you get the right answer. I think most of you have probably done quadratic equation type calculations at some point in your schooling. If not, Appendix A3 in the textbook does have a little bit of information too about it. But the big thing I wanted to remind everyone is one kind of interesting thing about the quadratic equation is this plus or minus notation in the formula. And what that means is you have to do the calculation twice. You have to do the calculation once, where you're saying that plus minus is going to be treated as a plus. And you have to do it again, where that plus minus is treated as a minus. And so one of the interesting things is you always get two answers. In this case, you get an answer of 2.32 or 0.935. So when you use that quadratic equation, you have to make a decision on what makes sense, okay? And so how do you do that? Well, let's look at those numbers that we have here. We have 2.32 and we have 0.935. Let's go back and take a look again at our initial table. Well, we said that our initial concentrations for H2 and I2 were 1 molar and 2 molar, okay? So remember those numbers, 1 and 2 molar. Well, we just did our calculation, and we're saying X is equal to 2.32 or 0.935. Well, how are we going to use this X number? We were going to use this X number in this bottom row here. We're going to take 1 minus X, 2 minus X, and then 2 times X to calculate those equilibrium concentrations. If I'm subtracting this from 1 or 2, if I subtract 2.32 minus 1 from 1, I get a negative number, right? Same thing if I subtract it from 2, I get a negative number. I can't have a negative initial concentration. That's not, that doesn't make any sense. And so because of that, it's telling me that it can't be this 2.32 value. Because my initial concentration is only one, the equilibrium concentration can't be negative. The initial concentration can't be negative. It just doesn't, from a just a common sense perspective, it doesn't make sense. So that tells me in this case that 0.935 has to be the value of X that I'm going to use. And so what I would do then is I would go back to calculate those equilibrium concentrations. I'd take my H2 concentration, which was 1 molar, subtract that 0.935 value, and I get 0.065 molar. Do the same thing with I2, 2 minus the 0.935 to get its concentration, and then the HI is 2 times that value based on that table I had set up initially. Then I get 1.87. So a couple things to remember on all this is just going back again through it. I needed to set up or make sure I have a balanced chemical equation. I wanted to set up this table of initial concentration expressed in moles per liter, change in concentration, and equilibrium concentration, all those in moles per liter. So I needed to check to see if I needed to do any what I'll say call mole math. So in other words, take the moles and divide by the volume. In this case, I didn't because it was a little bit easier problem because the volume was 1 liter. But I needed to get all that straight so that I could have this initial row filled in. And then I used the stoichiometry from that reaction to then decide, is it X, is it 2X, is it 3X, whatever. Once I get all that set up, then I think of that equilibrium expression, products over reactants. Any exponents are based on the coefficients in the balance formula, chemical equation formula. And then I plug the numbers in, and then I start doing the math on it, okay? Because I'm trying to get into this format to be able to use the quadratic equation and solve for X. I'll repeat this again. When you look at the math for the quadratic equation, I don't think it's necessarily difficult, but you have to keep everything kind of straight. Because it's easy to press a wrong calculator button or to multiply something too soon or divide too soon or subtract, you know, just that kind of what I would call bookkeeping part of doing something when you got a lot of numbers and you're putting it all into your calculator. So once again, make sure you do a few of these practice problems to make sure that you're comfortable with the calculations. And then remember on the quadratic, you got to calculate it 2 ways. You got to calculate it plus, you got to calculate it minus, and then you got to make a decision on which one makes sense, okay? And usually it's pretty clear which one makes sense. And in this case, we saw that if we used the 2 value, we were going to get negative numbers, and that didn't make any sense. So any questions on this type of calculation? Okay, great. As you might imagine, there's a very good likelihood something like this will show up on quiz, tests, things like that. So make sure you practice it a little bit. And like I said, really make sure that you get the calculator part down. You guys did a real nice job last exam on the natural log stuff using your calculator. And so here's another opportunity to do that again, to get good at the calculator part. Okay, so let's shift gears a little bit and talk about how you can kind of disturb equilibrium. And so Le Chatelier's principle says that if a system is at equilibrium and is disturbed by a change in temperature, pressure, or component concentration, and the component can either be a reactant or a product, that the system will shift equilibrium to counteract the effect of that disturbance. And so that makes sense. All it's saying is that you do something to the system, it wants to get back to where it was. And as I was telling the class earlier this morning, it's no different for chemical reactions, chemical situations, as it is like in your personal life. You think about it, you get upset about something, something impacts you, gets you out of equilibrium. What do people say? Calm down, relax, you'll be okay. It's the same, that's what this is saying with the chemical reaction, the chemical situation, is that the temp change, the pressure, concentration, all those are things that can upset that balance. And just like you want to get back to whatever your equilibrium state is, this does too. Okay, so what we can do is, from a qualitative perspective, we can predict what's going to happen. So remember, qualitative, we're not doing a calculation now, we're just saying if this happens, then what's going to be the result. Well, the key to this is remembering how do we write those equilibrium expressions? It's products over reactants, right? And so if we can keep that in mind, it's helpful. So like in this first example, where we have a change in one of the concentrations, if we think of it and we think of it as, if we increase the concentration of one of the products, the equilibrium is going to shift to decrease that and increase the reactants to get that balance back. If we increase the concentration of one of the reactants, it's going to drive the reaction towards the products, and once again, establish that equilibrium. Remember, when we talk about equilibrium constants, it's products over reactants, and so the numbers in those terms of the concentrations can certainly change, but that ratio is what has to stay the same. That's the equilibrium constant. And so if we have our little formula there and products over reactants, and that product one, for instance, increases, so then our numerator would increase, then something has to happen to get that ratio back in balance. And in that case, what happens is the reactants equilibrium would shift to push it towards the reactants. That's what you're saying in this one about concentration. If you have gases and you're talking about changing the volume or pressure, if you're changing the volume or changing the pressure, that really means you're doing the same thing, right? Because usually if you change the pressure, you're decreasing the volume. If you decrease the volume, you're increasing the pressure. So they're related. And so in this case, the higher volume or lower pressure, okay, favors the side of the reaction with more moles. And all it's saying, though, once again, is that you have, remember we said we can express the pressure equilibrium constants, pretty similar to what we did with the solution equilibrium constant, where it's products over reactants. You're really saying the same thing as we said for the concentration. Once again, if you do something that gets that balance out of whack, you've got to either increase the products or increase the reactants, shift it in those directions to get that ratio to stay the same as it was when it's at equilibrium. So that's all they're saying. That's all we're saying here on this one. And then finally, change in temperature. This is the one that I think is a little more interesting because you have to think a little bit, I think a little bit differently about what's going on here. Because the temperature one is interesting. It's not just that increasing the temperature or decreasing the temperature does something. It actually depends on, is the reaction exothermic or endothermic? So let's just think back to what those terms mean. If we say a reaction is endothermic, that means that we had to put energy into it. We had to put heat into it to make it happen, right? If we don't put that energy in, it's not going to go because it's endothermic. It requires energy to happen. If it's exothermic, we say that means that when it reacts, it actually gives off energy, gives off heat. So you can almost think of it as, in these examples, the heat is either a reactant or it's a product. Even though it doesn't necessarily show up in our balanced equation, that's kind of the way to think of it. So if it's endothermic, you're putting heat in, heat's kind of like a reactant, and that pushes the reaction towards the products. If it's exothermic, it's like you're forming heat. And so then adding heat, the products would be too high and it would push it back towards the reactants. So the thing that all three of these things that we just talked about have in common is we're really talking about balancing out concentrations in just different ways to make sure that the equilibrium constant is maintained. So those individual concentrations, individual things can change, but that overall ratio has to remain the same. And it wants to be, that ratio wants to be equal to whatever that equilibrium constant is. So the first two, concentration and pressure / volume, those to me are more straightforward in terms of concentration type and just balancing, pushing it to reactants or products. Change in temp's a little bit different, just because you got to think a little bit differently in terms of that heat, that energy that's either going in or coming out. You have to think of it as going in for endothermic reaction. You have to treat it as if it's a reactant, even though technically it's not. And if it's an exothermic reaction, the heat behaves as if it's one of the products, and you got to treat it that way. Okay, any questions about that kind of qualitative shift of things? Okay, so another way that we influence the reactions is through the catalyst. And remember, we talked about that the last few weeks. And the catalyst lowers that activation energy. And by lowering that activation energy, it makes it easier for the reaction to proceed. One of the key things to remember about this in terms of equilibrium is that catalyst, since it lowers the activation energy, it's lowering it for the forward reaction, but that's the same thing as the reverse reaction. So it's not just a one-way lowering for these equilibrium. It lowers it each way. So what I'd like to do now is spend some time going over some of the homework problems. And so once again, there's more homework problems than what I'm going to go over, but this will give you a feel for what some of them look like, a little more detail. And I would encourage you to spend some time working on these in general to get to where you're comfortable with them. And of course, can do the calculation. So the first one I'd like to look at is 15.13. And in this one, we're told we have a gas phase reactions, one A going to B and the other B going to A. And we're given rate constants for each of those. And then the first thing we need to calculate is the value of the equilibrium constant for A going to B. So for A to B, we're told the rate constant is 4.7 times 10 to the minus 3 inverse seconds. So that's the forward rate constant. Then the reverse rate constant, B going to A, we're given that value, 5.8 times 10 to the minus 1 seconds to the minus 1. And we want to find out what that equilibrium constant is. Well, in cases like this, where we're given the forward and the reverse, we can go and take that forward constant and divide it by the reverse, and that gives us an equilibrium constant. So in this case, 8.1 times 10 to the minus 3. So the key here is remembering this relationship, that forward divided by reverse. If we know those values, we can get the equilibrium one. Okay, then the next question of this for 1513 is, which is greater at equilibrium, partial pressure of A or for B? Well, if we write that equilibrium expression for the A going to B, remember it's products over reactants, so it'd be the concentration of B divided by the concentration of A. We know from part A that our equilibrium constant is 8.1 times 10 to the minus 3. So that what that tells me is if A and B concentrations were the same, this equilibrium constant would be 1. It's less than 1, right? Because it's 8.1 times 10 to the minus 3. So I've got some 1, 0.00, you know, we've got some zeros there, less than 1. If this is less than 1, then what does that tell me? It tells me that A has to be bigger than B. If B was bigger than A, then it'd be greater than 1. If A is bigger than B, that means my reactants have a higher concentration than my product. Just by seeing that ratio and knowing what my rate constant is, I mean my equilibrium constant is. So since the equilibrium constant is less than 1, the concentration of A has got to be bigger than B in order for that ratio to be less than 1. Yeah.
I'm just confused on why 5.8 times 10 to the negative 1 is on the bottom. And like the B to A reaction is on the bottom, and the A to B reaction is on the top.
Mm-hmm. So the question was, why are you talking about on part A? Yeah, why on part A did we have A to B divided by B to A? So that's just simply the definition of the equilibrium constant. It's the forward reaction rate divided by the reverse reaction rate. So that's why, and so since the equilibrium reaction that we're interested in is this, so the forward is A going to B, so the forward reaction is A to B, reverse reaction is B to A. So this was the keys that they told us that's the reaction we wanted to see. So that's how we picked out which one was forward and which one was reverse. If it would have been the other way, it would have been flipped. But this is simply this forward over reverse. That's simply the definition of equilibrium, equilibrium constant. I think it was last week, one of the days, we kind of worked through, and then in there it was, we packaged up some of these other constants and created the new constant, which was the equilibrium constant. That's where that all comes from. Does that help? Okay. Any other questions? Okay, let's go on to look at another problem. This is 15.15. So in this one, we're given a series of reactions, and then we just want to write the rate equations, the equilibrium equations for them. So let's take a look at the first one. So we have 3NO going to N2O plus NO2. So if we want to write the equilibrium expression for that, we've said we do that by expressing it as products over reactants. So we look at the products N2O and NO2. So we have N2O, that concentration, and these are all molar concentrations, times NO2, and then that's divided by the reactant concentration. So in this case, it's just NO. Then we go and we look at our balanced equation and see, are there any coefficients present? So we do have a coefficient in front of the NO on the reactant side. So then for NO, we're going to cube that concentration. So we get our final concentration of our final equilibrium expression of N2O times NO2 divided by NO, that NO concentration cubed. The other thing they wanted to know in the question is it a homogeneous reaction or a heterogeneous reaction? Well, homogeneous just means everything in the reactions, products and reactants are in the same phase. In this case, we're told they're all gases, so it's homogeneous. Let's look at the next one, question B. So here we have CH4 plus 2 H2S going to CS2 and 4H2. So we would look to see the products. That's the CS2 and the H2, that'll be in our numerator. The reactants, CH4 and H2S, are in the denominator. And then we look back at our balanced equation to see what coefficients we have. Well, on the reactant side, we have a 2 in front of the H2S. So that molar H2S concentration will be squared in the denominator. And then on the product side, we have 4 moles of H2. So that H2 molar concentration will be taken to the 4th power. And so our equilibrium expression winds up being CS2 times H2, the H2 concentration to the 4th power, divided by CH4 times H2S, the H2S concentration squared. Once again, this is homogeneous because everything was in the gas phase. So hopefully you're getting the hang of this. I'm going to skip down here to, let's skip down to letter E. Let's go to E. So with E, we have 2 Ag plus zinc plus 2 going to 2 Ag plus zinc. So on the reactant side, we have silver metal. That's what the little solid means. It's a solid material, so silver is a metal. So we have silver metal plus some zinc ions, and we know that's in solution because it's got the little AQ in parentheses to form silver ions, the Ag plus, that's in solution. We have the AQ, and then we have zinc metal being formed. That's the little S in parentheses. So if we go and write that equilibrium expression, our products would be Ag plus and zinc. Our reactants would be Ag and zinc plus 2. So we have Ag plus and zinc in the numerator, Ag and zinc plus 2 in the denominator. For some reason, I didn't write the Ag in the denominator and the zinc in the numerator. Why is that? Anyone know why that is? Remember, we talked about how if it's a pure solid or pure liquid, it has a value of 1. And so in this case, these solids, the silver solid, the Ag, the silver, and then the zinc, the Zn, those solids would, if I put them in that equation, they would have values of 1. Since they have values of 1, they don't impact the calculation. So in other words, they don't mean anything in terms of establishing the equilibrium value, constant value. So we don't write those in there, okay? So I don't write the zinc metal in, I don't write the silver metal in, and so that leaves me with Ag plus over zinc plus 2. The Ag plus in my balanced equation has a coefficient of 2 in front, so that Ag plus concentration, that molar concentration is squared. Zinc plus 2 doesn't have a coefficient in front, so that just stays as is. The other thing on this, because I have aqueous solution and solids, it's a heterogeneous reaction, so I've got more than one phase. Let's look at F here. This is another one that's a little bit different. So we have water over there on the reactant side, and then we have H plus and OH minus, so hydrogen ions and hydroxide ions. And then we want to write that equilibrium expression. So we have products, which is H plus, and OH minus concentrations in the numerator, and then we have H2O concentration in the denominator. But once again, I don't have anything in that denominator. The reason for that is, you see how the H2O has the little L in the parentheses? That's that pure liquid designation. And so because of that, just like on the previous one with the solids, we said, well, that value is 1. Because it's 1, it doesn't impact the calculation, and so we don't write it when we write that expression. So the first two we did were pretty straightforward. They were ones where you just simply take the products over reactants. Everything's in the same phase. You look at the stoichiometry of the balanced chemical equation, use that for the exponents on the molar concentrations, and you have your equilibrium expressions. The last two, we had examples of where, in the first one, in the E example, we had examples of where we had pure solids. And so those have a value of 1, so they don't show up in the expression. And then finally on F, we have pure liquid. And so that has a value of 1, so that doesn't show up either. Okay? So hopefully by the end of this chapter, you'll have drummed in your head products over reactants, and then looking at the stoichiometry of the balanced chemical equation to know what exponents you need to have. Okay, 1521, let's take a look at that. If the we're given the equilibrium constant for the reaction PCl3 plus Cl2 going to PCl5. And then we want to know what's the Kp for this reaction at this temperature. Okay, so one of the things we needed to remember was we want to find a Kp. And one of the formulas that we discussed last week was the one I have written here. The Kp equals Kc, so the regular concentration equilibrium constant, times RT, R is the gas constant, T is temperature in Kelvin, and then delta N. And remember, delta N was the number of moles of gaseous product minus the moles of gaseous reactants. So this is the formula that we use to convert from equilibrium constant based on concentration over to an equilibrium constant based on pressure. Okay, this is the relationship that we use. So we want to look at our formula, our balanced chemical formula, that equation, and we see it's PCl3 plus Cl2 going to PCl5. So what we see is for our delta N, we wanted moles of product. We've got 1 mole here, formed for 1 plus 1 is 2 moles of reactants. So for our delta N, 1 mole of products minus 1 plus 1 gives us minus 1 for that delta N value. So we've got our delta N value. Our temperature value, we just need to check to make sure it's in Kelvin. Well, in the problem, they said it was 500 K, so we don't have to do anything to that. We can just plug that 500 number in. Gas constant, we can look up, 0.08206. So we've got that filled out. We have the 0.042 value, which was our equilibrium constant for based on concentration. So we can put that in. And so we filled in all of our variables, and now we can go ahead and calculate out what that equilibrium constant in terms of pressure equilibrium constant is. And that's 1.02 times 10 to the minus 3. So for this problem, the key is remembering what that relationship is between Kp and Kc, and that's our formula. Kp equals Kc times RT raised to the delta N power. Remembering that that delta N is products minus reactants, using our chemical equation, our balanced chemical equation, to see number of moles that are in the product side and the reactant side. plugging all that stuff in, and then solving for KP. All right, 1531, let's take a look at that one. So in this one, we're saying that methanol is produced by reacting CO and H2. And we're told that it's a 2-liter volume. And we're given moles of methanol, CO, and H2. And we want to calculate our equilibrium constant on a concentration basis. So the first thing we want to do is we want to look at our balanced chemical equation. That's the CO plus H2H2 given us CH3OH. And we want to write that expression. Products over reactants, right? So product, CH3OH molar concentration, reactants, CO times H2 molar concentrations. We look at the stoichiometry, we have a 2 in front of that H2, so we have to take H2 to the second power, so to square that. So we've got that set up. Now what we need to do is what information do we have about the concentrations for the products and the reactants? Well, we were actually given the moles for each of those. So 0.0406 moles of methanol, 0.170 moles of carbon monoxide, 0.302 moles of hydrogen. So we got all that stuff. So that's a good start. But remember, to use this expression, this equilibrium expression, we have to be in molarity, moles per liter, not just moles. And we were told in this case that we had a 2-liter vessel. So we have to go and take each of those mole values and divide them by 2 to get molarity, moles per liter. We do that, and then we get these values of 0.0201, 0.085, 0.151, and those are the numbers that we want to plug in to our equilibrium expression, because that's the moles per liter values. We go ahead and do that and do the math correctly, and we get 10.4 as the value. So let me ask you this question. I asked the last class this, and no one answered me. But let me ask you, what's the units on this equilibrium constant? Did I just forget the units? I do that sometimes. It's a bad habit I have. The units for these constants, they don't have units. So I didn't forget. Okay. All right, 1543. Okay, 1543. So here we're told that our reaction is COCl2 going to CO plus Cl2. And we're told the equilibrium value is 2.19 times 10 to the minus 10. And then we're given a series of concentrations. And we want to know, is it an equilibrium or not at that concentration set? And if it's not, which way is the reaction going to go? Is it going to go towards the products or is it going to go towards the reactants? Remember we talked about calculating something called Q, and we said what Q was essentially the same setup as our equilibrium concentration setup. The equilibrium constant expression with products over reactants, that setup. The difference is that the values we put in for the molar concentrations are the values at that point in time. And so what it allows us to do is to see what our kind of like a pseudo equilibrium constant value is, the Q value is, given those concentrations. And then we can compare that to what the real equilibrium constant value is And based on that comparison, it tells us which way the reaction is going to go. So we have our reaction up on top. Then we can write that equilibrium expression. So products over reactants, once again, CO concentration times CO2 concentration divided by the CO2 concentration. There's our equilibrium expression. We were told that its value is 2.19 times 10 to the minus 10. Okay, and so now we were given some concentration values in the problem. And so we go ahead and we just plug in the CO, CO2, CO, CO2 concentrations into our expression. And so we get that, and what we see is we get the value, and for the first one, it's 1.09 times 10 to the minus 8. Well, is 10 to the minus 8 bigger or smaller than 10 to the minus 10? Well, 10 to the minus 8 is bigger, so that's a bigger number than a 10 to the minus 10th number. So if I go back and look at Q, it's products over reactants, right? So if this number, if this Q number is bigger than the equilibrium constant number, it's telling me that I have more products. Okay, because for that number to be big, products over reactants, the numerator's got to be bigger. And so what that means, we need more reactants. So that reaction, in that case, if we were monitoring it, it would start going towards the reactant side. Okay, in B, we do the similar type thing. We have our expression that we developed. We go ahead and plug those numbers in that they gave us in the problem. And we get a value of 5.5 times 10 to the minus 12 as our Q value. Well, 10 to the minus 12 is smaller than 10 to the minus 10, right? So that tells me the numerator is a little too small. So the reaction is going to go to form more products to make that Q value bigger, to get it on par with my equilibrium value. Finally, the last one, we plug those numbers, and lo and behold, we get 2.19 times 10 to the minus 10. We look back, and that was actually our equilibrium constant value. And so what that means is we're at equilibrium. Those particular concentrations maintain that ratio, which is what that equilibrium constant is, maintain that ratio, and so we're in good shape there. But what we're doing here in this problem is we're using that Q term that we talked about to do a calculation and then take that Q value, compare it back to the equilibrium constant value, and then that tells us which way the reaction for that set of concentrations of products and reactants tells us which way the reaction is going to go. Any questions about that? Okay. Okay, let's look at 4.7. So in this one, we're told we have Br2 going to 2 Br. We're given the equilibrium constant value, and then we're told that it's a 0.2 liter vessel. And now we're told that we have 0.245 grams of Br2, and we want to know grams of Br. Okay, well, one of the first things that we should have thought was, okay, we're not going to like those grams. Okay, so we're going to have to do something with that. That should have been the first thing that came to our mind, because remember, as we've talked about this equilibrium stuff, it's always been moles per liter, right? We talked about concentrations. So the grams should tell us we're going to have to at some point do something with that. The other thing that should have come into our mind is we have this vessel that's 0.2 liters. Okay, so it's not 1 liter, So when we get to that molarity thing, we're gonna have to do some correction for that volume part. So we go back and we look at our equation, BR2 going to 2BR. Once again, we write our equilibrium expression, products over reactants. So it's BR molar concentration divided by BR2 molar concentration. There's a 2 coefficient in our balanced chemical equation in front of the BR. So that BR molar concentration gets squared. Okay, so what we'd like to be able to do is fill in some of the spots there, because we know what Kc is. We were given that 1.04 times 10 to the minus 3. We were given grams of Br2. So we can convert those grams to moles using the molecular weight of Br2. So if we calculate that molecular weight, atomic weight of bromine is 79.9. So 2 times that is 159.8 grams per mole. We use that grams per mole to convert the grams of Br2. So by having the grams in the denominator here, we cancel that out. Now we have moles of Br2 in the numerator. Remember I said we want molar, moles per liter. That's where that 0.2 liter vessel information comes in handy. So now we can take those moles of Br2 and divide it by 0.2 liters, and that gives us a molar, moles per liter of Br2 concentration. And so that value would be 7.70 times 10 to the minus 3. Well, great. Now we've got another thing we can plug into our equilibrium expression. We have the constant we plug in. Now in the denominator, we're putting in this 7.70 times 10 to the minus 3. That leaves us with Br concentration squared. We can go ahead and solve for that. Let me move this thing again here. We can go ahead and solve for that. And it gives us a Br molar concentration, 2.83 times 10 to the minus 3 molar. So we're almost done, because remember, we were asked for grams, okay? And so now we've got to kind of back calculate from this molar expression to get it into grams. To set up the problem, we had to go from grams to molar. So we've kind of gone the other way, now we're going back the opposite way. So if it's 2.83 times 10 to the minus 3 moles per liter, if we multiply that by our 0.2 liter value, that's our total volume, then that gives us how many moles we have. Now we have moles of Br. We can use that atomic weight of Br to change from moles to grams. And then we wind up with the number of grams of bromine. And that's the 0.452 gram value. So this one was a little different. Usually we're just working in molarity, but in the problem they were asking us some questions about grams in that. And why would you do something like this? Well, in reality, you don't weigh out moles of stuff. You use a balance. What do you read? You read grams. So you think of terms of moles in terms of reactions and things like that. But when you think about actually doing the experiment, you're going to weigh stuff out. And so that's why someone would want, for instance, it expressed in grams rather than moles from a more practical perspective. But to make the equations and stuff work, you got to be in molarity. So a lot of switching back and forth. Okay, let's look at 1552. So in 1552, we have Br2 plus Cl2 going to 2BrCl. We're given the equilibrium constant, and then we're given moles of Br2, moles of Cl2, and we're told it's a 3 liter container. And then we want to know the equilibrium concentrations for the 3 components. Okay, so So in this one, we start with our equation, Br2 plus Cl2 blended 2 BrCl. And we write our equilibrium expression. So as we've said a bunch of times already, we have products over reactants. So we've got BrCl2 as our product, that's in the numerator, Br2 and Cl2, those molar concentrations in the denominator. We look back at the stoichiometry of the reaction and we see that 2 in front of the BrCl. And so we need to square that. So we've gotten our equilibrium expression written, products over reactants, we've got the right exponents on those. And next we're going to create that little table that we've talked about a bunch of times. So we have our initial row, we have our change row, we have our equilibrium row, and all of these are considered to be molar concentrations. And then we have the columns, the reactants, the Br2, the Cl2, then the product, the BrCl. And we know that we started out with 0.083 molar. Well, wait a second, that's not what we were told in the problem. Where'd that number come from? Well, we were told we had 0.25 moles of Br2 and 0.55 moles of Cl2. But remember, our volume was 3 liters, and we write these expressions, it's molarity, moles per liter. So we needed to do a little bit of prep work first before we could fill in our table. We needed to take for Br2, the 0.25 moles divided by 3 liters, and that's where we get the 0.083 molar value that is in the table. We did a similar calculation for the Cl2, for the chlorine. 0.55 moles of it divided by 3 liter volume gives us 0.18 molar. So that's an example of where we're filling our table. We don't want to get ahead of ourselves. We want to make sure that we have the concentrations expressed appropriately, and that's in moles per liter. And in this case, we had to go and take those moles value, which we were given, and divide by 3 to get molar, okay? So now we can put those into our table. Based on the stoichiometry of the reaction, we know X of Br2, X of Cl2 gives us 2X of BrCl. So we have a loss of X in the Br2 column, we have a loss of X in the Cl2 column, and we have a gain of 2X in the BrCl column. So that means our equilibrium concentrations for Br2 will be 0.083 minus X, Cl2 will be 0.18 minus X, and then BrCl will be 2X forming. Okay, so we've got those values. What we can do then is we can take those equilibrium values and plug them into our equilibrium expression. So remember, once again, it's products over reactants. So the product is that 2X value, that'll be squared because of that 2 coefficient on our balanced equation, divided by 0.083 minus X times 0.18 minus X. So we've got that all set up. And this is how we kind of got to in that example problem. But what I'd like to do now is just walk through the math in a little more detail to make sure everyone is on the same page with that. Okay. So there's some different ways you can go about the math in terms of what you do first. I'm just showing you how I did it. If you don't do it exactly this way, that's fine, as long as you know what you're doing and you can get the right answer. But in case you're a little uncertain, you can at least see an example of how I did it. So have my expression here, the 7 equals 2x, that quantity squared, divided by 0.083 minus x times 0.18 minus x. The first thing I did was I multiplied both sides of the equation by this denominator. So now I have 7 times 0.083 minus x times 0.18 minus x. I do that same multiplication to the right-hand side of the equation, so then that denominator goes away, and I'm just left with 2x, that quantity squared. Well, now the next step for me is to go ahead and do this multiplication of 0.083 minus x times 0.18 minus x. So the first thing I do is 0.083 times 0.18. That gives me the 0.149 value. Then 0.083 times minus x. That's this next term, minus 0.083x. Then I go back to the minus x term, minus x times 0.18 gives me minus 0.18 times x. And then minus x times minus x is a positive x squared. So that's where those four terms in the parentheses come from. It comes from multiplying that 0.083 minus x times the 0.18 minus x. Once I do that math, then I go ahead and combine the x terms, the minus 0.083x and the minus 0.18x. That's where the minus 0.263x comes from. So now the next thing I'm going to do is I'm going to multiply 7 times these three terms in the parentheses. If I do that, then 7 times 0.0149 is 0.104. 7 times minus 0.263 is minus 1.84. And then 7 times 1, of course, is 7. So now I get to where I have 0.104 minus 1.84x plus 7x squared equals 4x squared. Remember, I'm trying to set this up to be able to use that quadratic equation. So I want to get 0 on one side of the equation, and then the x squared x and the number terms on the left, on the other side of the equation. So to do that, what I would do is I can rearrange this so everything's on the same side. And if I do that, then I have, so in other words, I can subtract 4x squared from each side. So if I subtract 4x squared from the right-hand side of the equation, that leaves me with 0. If I subtract 4x squared from the left-hand side, then that 7x squared becomes 3x squared. The other terms, the minus 1.84x and the positive 0.104, those don't change. But now you see this expressed as 3x squared minus 1.84x plus 0.104. That's looking like that setup I wanted for the quadratic equation. So that's a step-by-step way of how I did the math. Like I said, you don't have to do it in that exact order, but that's the way I did it. That's kind of the way I like to do it. The key is to make sure that you can get from that equilibrium expression down to this final format to be able to use it in the quadratic equation. Any questions about that before I go on? Okay. Okay, so just to remind everyone, to use the quadratic equation, we said we wanted to have that ax squared plus bx plus c equals 0. We wanted that format. And that's what we see at the bottom of the page there. There we have that format. Okay. So now what we can do is we can use our quadratic equation. Once again, the quadratic equation itself was x equals minus b plus or minus the square root of b squared minus 4 times a times c. That whole thing divided by 2a. Okay? So now we want to plug in the numbers. So if our B value was minus 1.84, so minus B is plus 1.84. Then we have minus 1.84, that quantity squared. With our 4 value, our A term was 3, our C term was 0.14, so we fill all those in, and then 2A in the denominator, we have 2 times that A term again, which was 3. So we have all these things. So what we need to do is, we need to solve for the number under this square root function, okay? So we need to square the 1.84 and then subtract from it the 4 times 3 times 0.104, do that math and then take the square root of that. If we do that correctly, we should get a value of 1.46. So now we've got 1.84 plus or minus 1.46. The denominator is 6, that's the 2 times 3. And remember, when we do the quadratic equation, when we get to this step, we got to do it 2 ways. We got to do it where that plus or minus is a plus, and we got to do it where the plus or minus is a minus. We want both of those values. So let's go ahead and do that. And so if that plus or minus is treated as a minus, we get a value of 0.0633. If the plus or minus is treated as a plus, then that solves to be 0.550. So we get, once again, quadratic equation, we get 2 answers, and we have to make a decision on which one we like better, okay? You're not supposed to pick favorites, but in quadratic equation, you got to pick a favorite. So what did we say we do? We go back and we look at how we felt kind of started here. And we see that for Br2 and Cl2, those initial concentrations were 0.083 molar and 0.18 molar. We're going to then be subtracting this X value from those. So what were our choices again? Our choices were 0.0633 or 0.550. Well, if we do the 0.550, we're going to get some negative numbers. And we know we don't want that. So what that tells us is that that 0.550 value that we got when we use the plus is in the quadratic. That's not a reasonable answer. So we're going to use the 0.0633 number as our X value. So we go back to that original, we go back to this original box here and see for equilibrium concentrations, it'll be 0.083 minus that X value, 0.18 minus it, and then 2X. And so we do that math down here at the bottom. 0.83 minus 0.63 is 0.20, 0.18, 0.18 minus 0.063 is 0.12, and then 2 times that value is 0.13 moles. So now at the bottom, we have solved for the molarity of each of those products or reactants in our equilibrium expression. So those problems take a while to just wade through. For me, as you can see, it took me 2 pieces of paper to do it. It's tempting to do shortcuts. I would strongly encourage you not to. And just to talk for a moment or two again about this type of problem, you need your balanced equation. From that balanced equation, you're able to write the equilibrium expression with the correct powers on the different concentrations. You need to make sure, as you're setting up your little box there of initial change in equilibrium, you need to make sure that that initial step that you're expressing things in moles per liter, okay? So if you're given something in grams, you got to get it to moles. If you're given something that's not a 1 liter container, you got to get it moles per liter, all right? And that's what we had to do here. We had it in moles, but it was 3 liters, so we had to divide those moles values by 3 to get it moles per liter. You set all this up, and then that's where you get the equilibrium expression with the X's in it. Okay, that's where you get to show off your algebra skills and work through the algebra on that to get that final format that we want to be able to use the quadratic equation. And that final format, once again, is that a x squared plus bx plus c equals 0. We get to that point, then it's just a matter of taking those a, b, and c terms and plugging it into the quadratic equation, working through things, remembering that once we calculate what this square root term is, we have to apply it as both a positive and both a negative, giving us two answers, and then deciding, based on kind of the logic of what we're doing in the reaction, which one of those is correct. Once we get that, then we can go back to that table and apply that molar concentration that we said is correct, and do the subtracting or the multiplying or whatever we're doing to get what those molar concentrations should be. Okay? Any questions about this problem? All right, any questions about anything before I wrap up? I don't think we're going to get to the next chapter. So just to remind you again, on Thursday, we'll start the next chapter for the first part of class, and then we'll have a quiz on this stuff, this equilibrium stuff, chapter 15, with the rest of the class. And once again, as usual, it's an online Canvas quiz, so you'll need to log on and do that. So, all right, well, thank you.